We're going to listen to Hatami. He's from McGill, which is on the other side of the mountain. And he's going to speak about Borsuk-Ulam lower bound for sine rank.
All right, thank you. Okay, so in this talk, I'll talk about the new lower bound technique for proving lower bounds against sine rank. This really elegant and exciting parameter to sine rank. So before going into that, this is a joint work with two people, Kaave and Hosseini, who is a young professor at Rochester, and a student at McGill, Xiang, did this during the summer. Okay, so let's get to talking about sine rank. So we'll be talking about sign matrices. So we're interested in Boolean matrices, but when you talk about sine rank, it's more natural to think about pluses and minus ones, plus one and minus one. So those are sign matrices, and here we have a sign matrix of full rank, rank 3. Now, that's the usual rank, now over reals, let's say. Now, sine rank, what is sine rank? Sine rank allows you to change the entries to bring down the sign. But the restriction that there is that you have to keep the signs the same. So if you are a +1, you have to remain positive. If it's a -1, you have to remain negative. So let's look back at the same matrix. So like on the left here, we have the matrix, and here I'm changing the entries. So the entries, if you notice, they have the same sign. So all the positive ones remain positive, all the negative ones are negative. But now this new matrix has rank 2. So I decreased the rank from 3 to 2. So it's not a full rank matrix anymore. And the smallest we can get is called the sign rank of the matrix. So the goal is to decrease this as much as possible, keeping the signs the same. So it's a very relaxed condition, right? There's no need to be close to the original value. You only need to keep the signs the same.
You can't put stuff to 0.
So it doesn't matter. So it doesn't change it by much here, like by 1 at most. But there's another notion where you have also 0 entries, and then the zeros you have to keep 0, and that changes things drastically. But here, let's say no, everything remains strictly positive or strictly negative. And it's kind of without loss of generality. All right, so I'll just mention a few general areas where this appears. And I'll talk about the first two more in details after this. But like this notion, it's so natural, and it appears in so many places. So in learning theory, it corresponds to dimension, really, like the smallest dimension where you can represent your binary matrix. So I'll explain this a bit more. And there it's called dimension complexity by some people. Now, in communication complexity, so that's where actually it's formally defined first. It corresponds to this notion which is called unbounded error communication complexity, which is denoted by UPP at the matrix. And that's really captured almost precisely by logarithm of sine rank. So I'm going to use this notation rank with pluses and minus ones as for sine rank. Yeah.
Sorry, maybe you said the entries have to remain integer?
No, they don't have to remain integer. Yeah. So yeah, so you see this, if you're interested in this notion of communication complexity, which I'll define later, it's really basically a logarithm of sine rank. So it's a very elegant mathematical definition. Like you don't need to think about communication protocols and so on. It's just this notion of rank, and you take its log and gives you basically the exact value. Now, it's one thing about sine rank is that you can use it to lower bound many different things, including getting some circuit lower bounds. And it's really its power that can be used to lower bound many different things. And also, it's kind of a double-edged sword, because also it's a lower bound for so many things. It's very hard to prove lower bounds against it, because then you're proving lower bounds against many difficult things. It is also, so another area which is kind of, I think, a bit further away from the literature of complexity theory or theoretical computer science is this study of geometric graphs, where you define these things like intersection graphs, I don't know, like disk graphs and so on. So these are geometric objects on Rn, and you put edges, say, if the balls intersect and so on. And that's really like sine rank is kind of central there. It captures the dimension. So usually those things are objects of low dimension, like graphs of low sine rank, basically. So if you understand the structure of low sine rank matrices, then you can tell things about these graphs. And they use like techniques from algebraic geometry. It's quite a rich area. And another area, which there's this beautiful paper by Matuszek, which solved a very old problem, that he used Xiang to construct metric spaces that you can represent in any low-dimensional norm space, not just Euclidean, any norm space. And it's a very beautiful paper and uses it really cleverly. This was a problem that many clever people studied for decades, and initially, I think, asked by Johnson and Lindenstrauss, and then Bourgain had some partial progress, and finally Matuszek solved it. Okay, so these are a few applications. I'm going to talk about the first two and explain what that exactly means, and then I'll mention some open problems about them, and then mention this results. So let's go to this Xiang as a dimension, notion of dimension, so which is kind of appears in theory of learning. Okay, so let's go to the setting of learning. So we have this +1, -1 matrix, and think of it as some sort of a classification, binary classification thing. So for example, here you can think of this matrix as representing the following. Rows correspond to people, columns correspond to restaurants, and +1 means that the person likes the restaurant, and say -1 means that the person doesn't like the restaurant. Okay, so this kind of setting. Now, so let's try to model this, so some natural models. So one way to model these things is you can think of restaurants as represented by 3 numerical numbers, so features. So food quality, service quality, and let's say price. So every restaurant you model it, you represent it with these 3 numbers, like some ranking or rating for those things. And now people have different preferences, right? So some person might care more about food quality, some about price, some about service quality. So let's also model people by these 4 numerical features, which x1 to x3 tell us how much they put weight on each of these features, like food quality, service quality, and price. And x4 is some sort of a threshold. So let's assume that a person likes this restaurant if this weighted average of these things, so x1 times y1, x2 times y2, x2 times y3 is larger than their threshold x4, right? These coefficients can also be negative, like price is probably negative. You don't want to spend too much money restaurant. Okay, so that's some form of like representing this problem geometrically. Now, so this is really representing these things as vectors in R4, right? So every person is represented by these 4 numbers, x1 to x4, so it's a 4-dimensional vector. And every restaurant, so we represent it with y1, y2, y3, and -1. Now exactly here, the entry AXY is just the sign of this inner product, right? If you look at this inner product, it's giving you exactly this equation that you have. And if it's positive, the person likes it. If it's negative, doesn't like it. So we represented this matrix as this inner products, as the signs of these inner products in R4. Now, so with this, really think of this as this Xiang, so this will correspond to Xiang, is really the smallest dimension where you can do that, where you can represent your matrix as points and half spaces. So what do I mean by this exactly? So this is an alternative definition of Xiang, which is equivalent to the one that I had on the first slide. Xiang of a matrix is the smallest d such that you can find these vectors in Rd, and such that the entries are just signs of these inner products. So if you have that rank thing, so remember the first definition, I changed the entries of the matrix A to bring down the rank. And if you give me that matrix, I can decompose it and construct these vectors. So that gives you this representation. These 2 things are equivalent. And I'm going to normalize these vectors and assume that they're unit vectors. That's not going to change the signs, right? So I'm allowed to do that. So without loss of generality, we'll assume that these vectors are unit vectors. So there is this kind of trivial equivalence of this geometric notion of rank, dimension, and Xiang. And this thing about points and half spaces here is like in this picture, you can see. So if you think of this x, so that you have this vector pi x, and everything above it, so these are the ones y's that they get a plus sign, and these are the ones that they get a negative sign, right? So depending which side of this half space you are, half hyperplane you are, you get a plus or negative one. So you're really representing with points and half spaces. And that those representations are very common, right? Like when you do, say, support vector machines and so on, you represent vectors as points and half spaces. Okay, so I defined sign rank geometrically, but when you have this geometric representation, there's another natural notion which comes, again, very common in learning theory, which is the notion of margin, right? So if you look at this hyperplane, this hyperplane is dividing your points. That's the classification. One side are the pluses, the other sides are minuses. And you kind of want these points to be far away from this half space, right? So the half space is called decision boundary, and the points that are further away, it's kind of more clear whether they are plus or minus one. And when you're getting closer, it becomes more fuzzy, right? Like if you're very close to that threshold, it's not clear which side you are. So it's kind of desirable to have representations where the margin is large, meaning that all the points are far away from this decision boundaries. So that's the notion of margin. So I'll formally define it, but the thing is here now we don't care about dimension. So we are willing to sacrifice the dimension, go probably to a very high dimension in the interest of getting some large margin, so that all the points are far away from these half planes. Okay, so the largest margin we can get, that's called the margin of A. So more formally, if you give me a representation, the smallest inner product, the like absolute value of the inner product, that would be the margin of the representation. Like we represented things as this sign of the inner products, right? And you want those signs to be further away from zero. So you look at the smallest of those. And then you are interested in the representation that provides the largest margin. So you take the maximum of this or supremum over this over all representations over all dimensions. So you don't have to stick. I mean, these representations are not unique, right? You can go to a higher dimension, have a different representation.
It's really minimum there.
The infimum.
Xmi is discrete, no?
Well, I mean, these matrices could be infinite, like especially in learning theory, like you can think of this, yeah, okay, as being real numbers and so on. But for this talk, yeah, you can put a minimum there. Yeah, yeah.
Sorry, I don't think means why can't you scale psi up arbitrarily?
Oh, because we assume these are unit vectors. Yeah, yeah. So no, that's exactly for this reason that I assume they are normalized to be unit vectors. Yeah, you can't just multiply things. It's phi and psi are all unit vectors. Right. So we have this. So now think of these as both as capturing some notion of complexity of how easy your class is, your concept class. So one is psi rank. It means that your class can be represented in low dimension. So if psi rank is constant, let's say 10, it means you can represent it in dimension 10. So it kind of goes against this curse of dimensionality, right? So your number of parameters is small, then maybe the problem is easier computationally and so on. And then you also have this other thing of margin. You want margin to be large. And when the margin is large, you have algorithms that works well with those, like the classical perceptron algorithm, or more generally, these large margin classifiers like support vector machines. Those are, even if, no matter how large the dimension is, if your representation is has large margin, they perform well. Like they make smaller errors, and they're good in predicting things. Yeah, so it's like VC dimension is one way of saying a concept class is easy, and these are like two other ways, like psi rank and margin. Okay, so there is this interesting question which appeared in this paper of Lineal, Mendelssohn, Schechtman, and Schredman, 2007. So large margins seems to kind of indicate that your concept class is simple, like it's kind of hard to construct those things. And they ask, well, if your margin is large in some dimension, is your object like inherently low dimensional? Does it mean that you can represent it in low dimension in with some other representation possibly? So let's say if my margin is 0.1, does it mean that my psi rank is at most 10,000? Like I can bound it. So basically here we are interested in bounding psi rank as a function of margin, like only margin, nothing about the dimension of the matrix. Yeah, so this was a question that kind of started this work. Let's put that question aside. Now let's talk about communication complexity, and we'll come back to that question. So how does psi rank appear in communication complexity? So let me first tell you what the setting is. So in communication complexity, these sign matrices are your problems. So every sign matrix is a communication problem. So you have two players, Alice and Bob, and they know the full matrix. Like it's not like it's part of the input or anything. So that's your problem you want to solve. It's like similar, you want to solve SAT, so you want to solve this particular matrix. Now, what is the setting exactly? You have two inputs, X and Y, so which correspond to the row number and column number. So now you give the row number to Alice, you give the column number to Bob. And so Alice doesn't know what the column number is, and Bob doesn't know what the row number is, but they know the full matrix. Now, the goal is to find out, to talk to each other, to communicate, send bits back and forth to output something that's equal to the entry of the matrix, AXY. Okay, so one classical example is the equality, whether they want to know if X equals to Y. Right, so let's say your matrix is 1, if X is equal to Y, minus 1 otherwise. How much do they need to talk to each other to find out if X is equal to Y? Okay, so that's the setting of this two-party communication. And there's always an easy protocol, which is the trivial one, where Alice just tells Bob what row she got. So just sends all of X to Bob, and that takes log of capital N bits, and capital N is here, it's an n by n matrix. Okay, I'm going to use capital N to denote the dimension of the matrix. So my matrices are n by n. Okay, so there's always this upper bound that one player can send it to the other one, but for some problems you can do more clever things and actually talk back and forth and get the matrix. So I'm going to be interested in randomized protocols where Alice and Bob can also flip coins and do things randomly. Now here they just want to make a guess. They want to guess the value of AXY, and they want to be correct with, say, probability 1 minus epsilon. So there are a few settings, different settings here. Private randomness is probably the most natural in terms of communication, is that Alice has her own coins, flips, Bob has his own coins and flips, and then according to those, they communicate and then output something. And if they're correct with probability at most, if they're incorrect with probability at most epsilon for every possible input, then that's a good protocol. Okay, so that's private randomness. There's another notion which is mathematically nicer, and yeah, it's also very natural, which is shared randomness, which is they both see the same coins. So it's kind of nice because they know what the other person is seeing, like what kind of randomness the other person is using. So it's not completely blind to them. And this is mathematically nicer because you can think of it as a distribution over deterministic stuff, because you first like pick this random string for both of them, and then they just play some deterministic thing according to that, right? So yeah, so in this case, there's one string like that. And one comment is that achieving epsilon equals half is trivial. Like they can just completely ignore X and Y, flip a coin and output +1 or -1 according to that, right? So that's trivial. They don't need to talk at all to achieve epsilon half. So what's interesting is with this when this epsilon is less than half. And the standard value for epsilon is 1/3, which is kind of without loss of generality. So we can define these notions. This is private randomized communication complexity of A, which is the smallest cost to achieve error half, 1/3, sorry. Then you can define the same thing with public coin, which shared randomness basically. So that's when I don't put the superscript here, it means just public randomness. Now, so those two are, yeah, like when you want error 1/3. There's a third notion, which is the one that's related to sign rank, which is unbounded error. So here, the goal is just to beat 1/2. So, I mean, 1/2 was easy, just blindly output a random bit. But here, you want just to output something that has some intelligent guess in it, so anything. So you just want to achieve anything that's less than half. You're happy with that. So it's kind of limit of the first one when epsilon goes to half. So that's what it is. Now, this one you have to define it as private coin. If you define it with public coin, it's always like 1 or 2, like it's trivial. So this is called unbounded error. So those are three notions, and the relations that we have between these are the following. So the public one, of course, is stronger than private because they see each other's randomness. So that's a lower bound. We can do less communication to achieve this. So R array is always at most R private array. And of course, this UPP also is better than this one because here you want the error 1/3, but here you're happy with anything less than half. Let's say half minus 0.0001 or something like that. So both are lower bounds for private randomness. So each one of these two things have different strengths, right? So in this capital, in the public coin, the strength is that they have shared randomness. So they can use that. Here, they don't have shared randomness, but the requirement is very relaxed. They just want to be better than half. Yeah, so, okay, so let me mention, so why is this related to what we are talking about? So Patrick and Simon, who defined Xiang actually, the purpose was to study this thing, this latter notion, the UPP, unbounded error, and they proved that, yeah, unbounded error is basically logarithm of Xiang. So it has a very elegant mathematical characterization, unlike the other notions of communication complexity. And one thing which is important for this talk is that, so I mentioned that public is a lower bound for private, but this lower bound is not off by too much. So there is this lemma, which is called the Newman lemma, which says that you can pay a cost of logarithm of, so it's log of capital N. So I wrote it in small n. And that's how much you need to pay at most to go from public to private. Okay, so they are kind of within a log n additive factor of each other. And the reason I write this in small n, like log of n, because in communication complexity, it's natural to think of this small n as your actual parameter. If you think of inputs as n-bit inputs, then this is your matrix is really 2 to the n by 2 to the n. So from this, you get also that, of course, UPP is at most public randomized plus log n. So because even private satisfies. Now, I mean, how do these two things compare? So in an earlier work, like from 2019, with Kaave again and Shakalovet, we proved that the gap can be actually, like this inequality could be very, the gap can be huge. So as much as large as possible, really. So there are examples where Xiang rank is only 3. The UPP is really constant. And the randomizer is as big as possible, basically. It's big omega of n. So that's the upper bound we have, right? So the gap can be huge in that direction. In the other direction, we know the gap can be at most log n, but we don't know exactly what it is. And that's the question I'm interested here. Yeah, so is there, like, how large this gap can be? Can we have things where, the other direction? Where R is small and UPP is actually large. And the problem with this question is there are very, very few techniques for proving lower bounds against Xiang rank. Actually, there are like only 3. Like it's VC dimension, Forster's approach, and then there is also something which they contain a large monochromatic rectangle. So there's only 3 known techniques. There's also a counting technique, but that you can use against explicit matrices. And none of those, so all those techniques also give lower bounds for R. So if you want to prove UPP is at least whatever, like log n, the same proof is going to also show that R is at least log n. So it's really, none of those are suitable to studying this question. Okay, so this is the problem I'm asking now. Is it true that if bounded error is small, then UPP is also small in this sense? Like if it's at most 100, then can you say also Xiang rank is at most some constant? Okay, can you bound Xiang rank in terms of just R, like randomized communication complexity? And yeah, so these techniques really can't, I mean, we believe this is not true. And these techniques, none of the known techniques can solve this. Okay, so, and this question is equivalent to the earlier question that I wrote. So these two questions are like exactly the same question.
Sorry.
Yeah.
I lost it. What is RA again?
Just public coin randomized communication complexity. So you want to, yeah, you have shared randomness, Alice and Bob, and how much do they need to communicate to get error 1/3? Unbounded error, yeah, but it's in private coin. So that's why Yeah.
And because like trivially RA would be bigger than UPP.
Yeah, so
If I had the same type of coin.
yeah, exactly. If you had the same,
Really a coin difference here.
yes, that makes it otherwise, yeah, it's trivial.
And what is the, if you have like a algebraic description like you have for UPP in terms of sign ring for RFA?
So margin, not algebraic, but it's
what's the
geometric.
function?
Yeah. So these two questions are equivalent because of that. So UPP, we already saw that it's equivalent to psi rank, and randomize is equivalent to margin. There is an exponential gap, but here we don't care about those things. It's really about constant versus non-constant. Okay. So if you have, yeah, small randomized, you'll have large margin and vice versa. Okay. Yeah, so here is a great problem. I spent like 2 months thinking about this. Didn't go anywhere, but I think it's really a fantastic problem. It's a candidate to solve this problem. Just hypercube. So this is a 2 to the n by 2 to the n matrix. It's the usual hypercube, really. And you put a -1 if your Hamming distance is exactly 1. So like it's the adjacency matrix of the hypercube, but turned into pluses and -1s instead of 0s and 1s. And yeah, the question is, can you show that the psi rank is not bounded? It grows as you increase n. I mean, it can get better than this, right? It's a hypercube. It's like so much structure. It's a nice matrix. And my expectations are low too, right? Like I don't need a strong bound. I just want to show that this rank grows. It's proved like log a star and whatever, like you can. But yeah, it's open. It's a hard problem. It's because of exactly what I said, like the lower bound techniques for psi rank can't solve this. So you have to invent a new lower bound technique if you want to solve this. And yeah, we know nothing really, like in terms of upper bounds too. There's an obvious upper bound of n, and that's all we know, which is not sharp because in Q2 you can do 1. That's all I know really. Yeah, and lower bounds, I think I know a lower bound of 4, so you can get to 4, but I can't prove 5. That's all, you know. But yeah, so it's a fantastic problem. Like I think if you get a chance, you should think about this. Right. So yeah, why is this a candidate? It's randomized communication complexity is 1. So if you prove this, then it solves both these questions in the negative. So yeah, like there is no reason for it to be bounded. Like it's yeah. So that's why it's very natural to conjecture that it grows to infinity. It's just we don't have the techniques to prove these things. Okay, yeah, and that's already mentioned. All these Forster's method, like rectangle method, VC dimension method, they just show that your rank is at least 3 or 4 or something. You can't get anything better than that. Okay, so yeah, like I spent quite some time working on this, and then yeah, like we managed to solve this for partial functions, and yeah, with a new technique too. So we thought maybe we can solve the total one, but still haven't been able to. Okay, so now we move to partial matrices. So exact same setting, pluses and -1s, but now some entries are just stars. So no restrictions there. Like for example, if you define psi rank according to original definition, you can do positive or negative on these stars. We don't care. So bring the rank down as much as you can. The same with communication. So those entries, if Alice and Bob's X and Y corresponds to those, they can output anything. We're happy with anything. So those don't count as errors. So you can ask exact same questions here. Is it true if margin is large, then psi rank is, are there matrices where margin is large, but psi rank, say small? Yeah, large and psi rank is also, psi rank is a small thing. And yeah, are there matrices where randomized communication complexity is small, but UPP is large? Now, there's a natural candidate. And it's quite nice, this whole thing, because if you come from the perspective of communication complexity, it's not so clear this is a natural candidate. But then when you see the equivalences go to this margin and psi rank, then this becomes a very natural candidate here. So the gap Hamming distance. So this is my partial matrix. It's 2 to the n by 2 to the n. I have a plus if the vectors are almost the same. So they're very close. The inner product is almost full. It's almost n, so 0.99 n. And it's -1 if they're almost antipodal, like their inner product is almost negative n. Okay, and otherwise I don't care. So these are things which have large margin, basically. They're far away from being orthogonal, right? So it's kind of by design, it has large margin. I said it's equivalent to randomized communication complexity, but you can also see that randomized communication complexity is small here. Basically, what Alice and Bob can do is just sample a few coordinates and compute an estimate of the inner product according to those coordinates. So you just sample some S publicly, so they both see the same S. They don't need to communicate for that. And then just do this inner product. And if they see most of the time xi is equal to yi, then of course they're going to think that they're in the first case. If most of the time x and yi are different, then they are in the second case. It's just a simple probability calculation. So that's the randomized protocol. Oh, what about psi rank? Psi rank is already n this from just this representation. This is a representation, right? You're representing x and y with vectors in Rn. Now the question is, okay, so can we prove a lower bound for this? Can we show that psi rank grows? So for geometrically means that for the stars you don't care, like you don't have to match the sign of the inner product doesn't have to match anything, right? And the first definition too, like when I was changing the entries, so I had this restriction that the signs have to be kept, right? Plus ones have to remain positive, negative ones have to remain negative, but the stars you can put positive or negative, doesn't matter. So can we prove any lower bound for this? Now, most of the lower bound techniques for psi rank are analytic, like they use geometry, like convex geometry, like Forster's proof, for example, puts the vectors in isotropic position and then uses spectral techniques there. So yeah, but the key to solving this question turns out to be topological. Okay, so this is what we proved. We proved quite a sharp bound here that the psi rank is actually linear in n. So I mean, we have the upper bound of n, and we can prove a lower bound, which depends some constant times n. So at least for partial functions, this solves those problems. We have something that has large margin. Margin is 0.99. Psi rank is theta of small n, which is log n. And then randomize also, you get, randomize is 2, but UPP is theta of log n. Remember the Newman's lemma that I mentioned earlier, that UPP is at most RA plus log n. So this works for partial matrices too, and this shows it's sharp. So this log n, you really need the log n exactly there. It's even when you use UPP. Okay, so you can't find better examples. Okay, I think
so this partial problem seems to have less constraints. So I don't see why this gives you not a lower bound on your problem without the stars.
Oh, the issue is you want also RA to be small, right? So it's not clear if you can fill the stars with plus ones and minus one to keep the RA and still keep the RA small. Like it makes it easier for both R and UPP, or for both psi rank and margin. And you fill the stars and then suddenly margin becomes difficult or R becomes difficult. Okay, so one other thing I want to say about sharpness of this is, so Johnson-Lindenstrass lemma says that if you have a bunch of points if you have n points in any Euclidean space, you can project them to dimension log n and without messing up much by the distances, right, with low distortion. And you can use that, like if you have large margins, then if you don't mess up the distances by much, the sign of the inner products remain the same. So from that, you get this bound that psi rank is at most some function of margin times log n, but you have to pay this log of capital N and use Johnson-Lindenstrass. And again, this question that was asked by Lineal, Mendelssohn, Shechtman, and Schroedman is this log n actually necessary here? And our example shows it's necessary. Like you actually need all log capital N there. For partial functions. Again, for non-partial functions, we don't know. Like hypercube is one example that we can analyze. Okay, so let's go to the actual proof. So it's amazingly, the proof is so short. Like, I mean, I have very little time, but it's enough to tell you all the proofs. So Yeah, so the key is to look at continuous setting. So instead of looking at that gap Hamming distance, we just look at all of the sphere. So I'm defining this gap inner product function, which takes 2 points on the n-dimensional sphere, so Sn minus 1, which is an n-dimensional sphere in Rn. So you take x and y and you look at their inner products, right? These are unit vectors, so inner product is between 1 and -1. So if it has large margin, if it's the inner product is larger than gamma, I'm going to be 1. If it's less than gamma, I'm going to be -1 and still otherwise. So it's an infinite by infinite matrix, like it's indexed by s to the n minus 1, like the sphere. Now here, so what we prove first is that here the sign rank is full. So I mean, the sign rank is n in this representation, like, so it's at most n because of this representation, and that's the best you can do. So you can't even bring down the sign rank by 1. So you get exact n. And I mean, of course, you can't prove something like that in the discrete case. It's not true. But here, yeah, you get exact sharp map. And that's kind of a good, I mean, if you see this result, you know the approach shouldn't be analytic. It should be topological, right? Like how else you can get exact number n here? Okay, so how do we prove this? Okay, so key is this theorem, Borsuk-Ulam theorem, which is quite an amazing theorem. It has many unexpected applications, like it's all over the place, weird applications to like graph colorings and so on. Here is what this theorem says. It says that if you take the sphere in Rn and map it to 1 dimension lower, so Rn minus 1, like flatten it with a continuous map, then there will be 2 antipodal points that's going to go to the same point. So that picture is from Matuszek's book. So Matuszek has a great book on this, about these applications. So here, yeah, you have someone who holds a ball and just crushes it, puts it on the ground, and it says there will be 2 antipodal points on the ball that just now on top of on top of each other. Okay, that's the theorem. And I mean, the map has to be continuous to be true, and it has many different forms. It's not. I mean, this is one form of the theorem. Has many equivalent forms and many amazing applications. Yeah, it was always one of my goals to use this somewhere. But finally, it's every problem I have, I check it. And finally, it works. Okay. All right. So how do we prove this? It's like, I mean, now we don't have to do anything really. Just Borsuk-Ulam is going to prove it for us. All right. So what are we trying to prove? We're trying to say that you can represent this in dimension n minus 1. And what does not being to represent here means? It means that there are no maps phi and psi which take our vectors on the sphere and maps them to Rn minus 1, such that if the inner product is larger than gamma, we want to remain positive. If it's less than minus gamma, we want to be negative, right? That's just the meaning of the sign rank representation. Okay, so yeah, that's what we have. Now, just let's plug y to be the same as x. So from these, you get that phi x psi x has to be positive because the inner product is 1. And this one has to be negative because the inner product is -1, right? So we get these 2 things have to hold. Now, if phi is continuous, we're done by Borsuk-Ulam. That can't be the case because then there will be 2 antipodal points that are going to the same place, but then these 2 can't hold, right? So because phi x is the same as phi negative. So if phi is continuous, we just, yeah, it's Borsuk-Ulam. I wouldn't be surprised if it's actually equivalent to Borsuk-Ulam, but yeah, I didn't try. Okay, so that's the continuous case. But what if phi is not continuous? That's also, it's not that difficult. We're going to make it continuous. So to make it continuous, we take an epsilon net in Sn minus 1, a finite epsilon net, and then kind of define this new map phi tilde as the following. So for every point x, you look at all the points in my epsilon net, and I'm kind of average the ones or add up those ones that are close to x in a continuous way. So for every z in t, I take phi of z and multiply it by some function of the distance. Now, to make this continuous and local, what I need is that this rho is continuous, then this will be continuous. And what I have here is that if you are closer than epsilon, it's 1. If you are larger than 2 epsilon, it's 0. So they don't appear in the sum. So everything is local in this 2 epsilon neighborhood. So that's, yeah, so it's a continuous map and it's there. And it's easy to verify that it doesn't mess up with our condition by much. So if the original one was working with gamma, this will work with gamma plus 2 epsilon. So yeah, so that's really just, that's the whole proof of this thing with Borsuk-Ulam. Okay. Yeah, very short proof. Now, I mean, back to discrete cube. So discrete cube is not exactly n, so we have to work a little bit here. So in the discrete cube now, we want to prove a lower bound, which is linear in n, and that was our function, right? If the inner product is larger than 0.99n, then +1, and in this case, it's -1, and there was a star, I didn't write it here, just for the space. Now here, we're going to embed this continuous one in the discrete cube. That's what we're going to do, but we're going to pay in dimension. So we're going to pick a d, which is smaller, delta n, and kind of blow it up to this larger n. So the way we're going to do is take an epsilon net in s to the d of, say, minimal size. This is going to be of size roughly 1 over epsilon to d. Do this randomly in the following way. Just pick random vectors, wi in SD, n of those, and define this map. So I'm mapping x to sine of inner product of x of wi. So I'm just throwing these cuts in the sphere, and depending on which side you fall, I'm going to put a +1 or -1. And these are random cuts. And because I put in a lot of these cuts, like n of those, that's going to keep the inner products. Like if you're close, you're very likely to end up in the same side on most of the cuts. And if you're almost antipodal, you're going to be ending up in different side. So this kind of works for everything in T. They're going to have a nice embedding, and then you can extend this to all of the sphere by just locally. Like you just pick your nearest thing in your epsilon net and just follow that. So yeah, so that's the thing. It's kind of yeah, initially we had a worst bound because we were doing it deterministically, but yeah, with this random vector, it gives you a linear bound, which is shocking. Okay. So there's a bit of detail missing, but it's something I'm sure everyone can do if you sit for half an hour. It's like an easy thing. Yeah, so that's the other one. So yeah, I'll end with two open problems. One is, I've already mentioned, this hypercube. Just want to advertise it's a great problem. There's another open problem, which is, I think it's quite an important problem, and it's linked to some deep stuff in math. I don't know how many are familiar with this gamma 2 norm. I'm going to tell the definition just below that. But here's a question. So if your Boolean matrix, if your sign matrix has gamma 2 norm constant, then can you embed it in constant dimension? Does it imply that sign rank is constant? Okay. Now, gamma 2 norm is the following. So now I'm representing my matrix, instead of the sign, is actual inner product. So A of x, y has to be inner product of phi x, psi y. So there's no sign here anymore. And my quantity that I'm trying to optimize is that how large these vectors are. So you look at the maximum of the phi x, psi y over all x and y. So this is one way of defining gamma 2 norm. You can define it in different ways too. And you have to look at the product because you can always like divide one by C, multiply the other one by C, right? It's just the inner product. Yeah.
L2 norm?
Yeah, it's L2 norm. Any dimension. Yeah, so you can pick n is enough. If it's an n by n matrix, you get this you can get it in dimension n. But I mean that's the question. Why is it related to the previous thing? Is that this margin of randomized communication complexity, they're actually equivalent to approximate gamma 2 norm. So for those, we saw this doesn't hold. But if instead of approximate gamma 2 norm, if I use gamma 2 norm, maybe it holds. Okay, that's the question. And it is, so one reason I like this question is we can verify it for a large class of matrices, this lift matrices, which are the following. Suppose you have a function from a group. This could be a locally finite, even infinite group, but let's say G is a finite group. You have a function on a finite group, so maps it to +1 and -1. And you define your matrix as f of x times y inverse. So an example of these matrices are the XOR lifts, right? So if you're working over Z to the N, then this XY inverse is just XY, which is just XOR up to 2 vectors. Okay, so a large class of matrices fall into this thing. And this theorem holds for those classes. And the reason that it holds is there's deep reason. So there's this theorem of Cohen from 60s, which characterized idempotence of Fourier algebra. And then more recently, like in 2000s, Green and Sanders proved quantitative versions of those theorems. And those give you structure of these, like you can get a nice structure, but these functions, you can characterize their structure. And from that, you can get that this sign rank is bounded. So this large class of things is true with these theorems, which have quite complicated proofs. And the proofs don't generalize to arbitrary matrices. So it's quite an interesting thing to understand. Like, do you actually need this group structure, or it's a more general phenomenon? Yeah, so that's the last open problem I wanted to mention. Yeah, I think both these questions are important and quite nice things to work on. Yeah, thank you.
Thanks. Questions?
Yeah.
Yes, so this type of matrix, the bullet, I believe Cohen and Zhao show that for these type of matrices, you see the growth norm, which is like the dual of gamma 2 is equal to n or 1 over n times the operator norm. Is that all related? So it seems related to Cohen, Green, and Sonic.
Wait.
It's so that these
The dual is okay. Yeah. So the relation is that the operator norm is equivalent, yeah, exactly, to the dual of gamma 2. So that means the gamma 2 norm becomes equivalent to this algebra norm. Like in terms of the Fourier, it becomes the sums of the absolute values of the Fourier coefficients. Like if it's G is a finite, if it's G is an abelian group, right? So this Green and Sanders theorem characterizes functions have bounded Fourier spectral norm, right? So they're in this coset ring, and then from that you get this sign rank is bounded. Yeah, so it's a lot of, yeah. Any other question? Thank you.
Have one.
Oh yeah.
Yeah, in the tensor setting, what often happens is that people study like asymptotic parameters. So meaning this setting would be start with a sign matrix and you take a tensor power.
Mm-hmm.
And then you wonder, how does the sign rank, how does it grow? Because there's something interesting happen there?
Yeah, so if you tensor two matrices, their sign rank multiplies.
Oh, it just
so
then it's
you can bound it. Yeah, I see what you're saying. Yeah, it's at most a product, not exact. Yeah, it might drop probably. Yeah, I don't understand.
Will it drop all the way down? Or?
Yeah, I don't know. Actually, I haven't thought about it.
Okay. Thanks.
Yeah, thank you.